We are now about to begin our third session, covering a few more use case presentations. So if I could quickly ask everyone who is presenting in this session to hop on up here and grab a seat, that would be lovely. All right, so the format for this session, very similar, of course, to the previous one that we had just before lunch. So we'll have 3 different specific presentations. If you do have questions, please either write them down or keep them in your head. Once we're at the end of the 3 presentations, we'll open up some time for Q&A. We do ask in advance, so of course, follow-up questions are lovely. Keep those in your head and follow up with the person after, because we'd like to be able to get through as many questions as we can. So hopefully you can hold yourself back with some pressing questions. So first up, we have alternate wetting and drying for irrigated rice in Bangladesh. That will be presented by Kunwar, Singh, and Reeya, Shrestha. So Kunwar is a senior geospatial scientist at AidData and an affiliate faculty member at the Center for Geospatial Analysis at William & Mary. His research advances the use of geospatial data, remote sensing, and drone technologies to evaluate the impacts of development and environmental interventions. His work focuses on food and water security, climate resilience, and geospatial impact evaluation across South Asia, Sub-Saharan Africa, and the northeastern United States. Joining him will be Reeya Shrestha. She is a master's student in geography and environmental sustainability at the University of Oklahoma. Her research focuses on the use of geospatial techniques and remote sensing for water management in agricultural systems.
Good afternoon, everyone. It's really a torture after giving a talk after lunch, and after pies, and not 1, 2 pies, it's really tough. So, thank you, Matt, for the introduction. This work is in collaboration with Professor Kyle Emmerich. He's from Tufts University, and I will be presenting this work with Reeya Shrestha. Matt already introduced us. We used Earth observation-derived evapotranspiration estimation method to measure and evaluate a climate-smart agricultural practices known as alternate wetting and drying. Hereafter, I will use AWD in Bangladesh. Rice cultivation is one of the most water-extensive crop in the world, and Bangladesh is one of the areas where rice cultivation happens in a huge area. Millions of farmers depend on irrigated rice production for their livelihood and food security. However, increasing pressure on groundwater resources, rising energy cost, and climatic variability make efficient water management more important than ever. This raises a fundamental question: can farmers reduce water use without compromising agricultural productivity? This is one of the use cases where we literally had to go out of our comfort zone and find something innovative that we can bring in to do this study and produce something innovative. And that is evapotranspiration estimation. Going back to the question, can farmer reduce water use without compromising agricultural productivity? One promising solution is alternate wetting drying. Instead of continuously flooding rice field, AWD allows field to dry to a certain threshold before irrigation is applied again. Farmers monitor water level using a simple field pipe, and irrigate when water falls below approximately 15 centimeters. The concept is simple: use fewer irrigation while maintaining yields. Agronomic research from Bangladesh has consistently shown that AWD can reduce water use without negatively affecting production. But demonstrating agronomic potential is very different from understanding adoption and impact at a scale. To understand whether farmers would actually adopt AWD, researchers implemented a large randomized control trial across 400 villages in Bangladesh in 2017, 200 treatments and 200 control villages. The study covered three major rice-growing regions: Rajshahi, Rangpur, and Myanmar Singh. And there were 10 farmers per village. Treatment villages received AWD pipes, training, and installation support, while control villages continued with conventional irrigation practices. During this randomized control trial period, researchers, Kyle's team, had 2 unannounced visits per plot and selected during the random days. One of the most interesting findings from this study was that AWD did not affect all farmers equally. The intervention was most effective among farmers who paid volumetric water price. In these settings, conservation water translated directly into lower irrigation costs. Researchers observed lower water level and drier field among treated farmers, but primarily where economic incentive existed. For example, on a upper left figure where you see blue line with the treatment, there are there were lower water levels, and the next figure here you will see a field in a dry, basically means a dry field among treated farmers. As I mentioned, the finding highlights a broader lesson in development. Technology alone rarely drives change. Incentive often determine whether innovations are adopted and sustained. Based on this randomized control trial, Kyle and his team carried out a second randomized control trial between 2019 and 2022 across 360 villages. 45 of them, they were in control. 45 out of 360, they were control villages. This study focused on scaling strategies. Researchers tested different approach for introducing AWD, including direct outreach to farmers, community meetings, and engaging through irrigation owners. So basically 3 groups: door-to-door meetings and owners. All treated plots, basically they had electricity bills. So researchers used electricity consumption as a proxy for water extraction. So what it means is that lower electricity bill means lower water consumption. The findings were compelling. AWD reduced electricity use for pumping by approximately 30 to 40%. This provided a strong evidence that farmers were indeed using less water. Now, together these 2 experiments provided a strong evidence on adoption and water-saving behaviors. But they also raised few questions. Can we observe these impacts beyond individual villages? Can we evaluate whether benefit persists over time? And can Earth observation help us move experimental evidence to landscape scale evidence? And this became the motivation for our geospatial impact evaluation for this use case. Traditionally, measurement of water consumption relies on field survey, direct measurements, and site visits. So imagine in order to track how much water farmers they are using, either we go visit in the field and see and measure the water height during the flooding period. Another way we can use electricity. And this is where Earth observation came into play, we wanted to know if Earth observation can directly use to estimate water consumption. And this we carried out through evapotranspiration method. And I'll pass presentation to Reeya, who will talk further how we use Earth observation to carry out impact ET estimation.
So thank you, Dr. Kunwar. We now know that from field measurements that AWD farmers used like less electricity, which means that there was like a considerable water saving happening there. So the next step was to see whether those saving could be measured from space at different scale. So with that, I'll be introducing you one of the ET models that we used in the study and how it was validated and also the impact it has in the Bangladesh AWD study area. So before that, let's dive into the term evapotranspiration. So in general, evapotranspiration is like the combination of evaporation and transpiration, meaning that the water lives in two different ways in the agricultural field, and they are not equal. So transpiration, it can be termed as a productive water use, meaning that the water gets lost from the plant. And evaporation, in the other hand, is the loss of water from the soil, so which can be termed as like the non-productive water use. So the model that we use is the Shuttleworth-Wallace two-source model, which kind of separates that evaporation and transpiration, as well as it also gives the estimate of the combination evapotranspiration. So that partitioning is what makes it possible to detect the effect of AWD through a satellite. So in general, this is like a general overview of the model. So the two key inputs that gets fed into the model are the weather data, and another one is the satellite image. So for the weather data, we generally use like wind temperature, solar radiation, humidity, whereas for the satellite image, we specifically use the Sentinel-2 image that has the resolution of 10 meters and also has like a revisit time of 5 days. So with that input, we kind of like, derive the vegetation information and also use the equation to calculate the ET. So the good thing about this is that all this part can be run in Google Earth Engine, which is, does not require like local computation, and also it is scalable. Also, running this model in Google Earth Engine means the model produces daily maps of the total ET, plant transpiration, and soil evaporation for every field in the study area. So for Bangladesh, that output covers all the AWD rice plots across the study region, season by season. And also at 10-meter resolution, individual field boundaries are also clearly visible in the map. So before applying this model in Bangladesh, we applied this model in California vineyard. So that is where we validated this model. So the first thing that we looked into was the weather data. So not every region has the dense ground station networks. So the model in the California vineyard was tested with 4 different weather inputs. One was local tower, another one was regional station network, and another one was 2 gridded reanalysis products at different resolution. So the spatial patterns of ET kind of stayed consistent, but the better results were shown with the use of local weather data. And the second was the study area size. So the model was also tested at 4 domain sizes, which ranged from 4 by 4 kilometers to 24 by 24 kilometers. And the performance, it did not change that much, meaning that the model ran accurately over a small cluster of fields as it does over a large region. So both findings matter for Bangladesh, where we have used the AGERA5 gridded weather data, and it also covers like over 90,000 plots, which is like a vast geographical region. So these maps show 3 different growing seasons from 2019 to 2021. So on the color scale, the blue region kind of represent the high evaporation loss, and the red region kind of represent the efficient water use. throughout the field. So this E over ET ratio is a useful indicator, meaning a lower ratio means that the less water is being lost from the soil and more is going towards the actual crop use. So in AWD fields, we expect this ratio to be lower than in continuously flooded fields. So this ratio, E by ET and transpiration by ET, are complementary ratios that always sum to 1. So when AWD reduces soil evaporation, E by ET decreases and T by ET increases, because T by ET represents the fraction of water used by the crop for growth. It serves as the key outcome variable information for treatment effect analysis. So this will be explained by Dr. Kunwar further.
So let me reiterate a few things. Transpiration, evaporation, and evapotranspiration. There are 3 technical words. Transpiration represents productive use of water by crop. Evaporation represents water lost directly from the soil. And evapotranspiration, they are a combination of both transpiration and evaporation. The data after this analysis, we used that is transpiration by evapotranspiration. If we want to get evaporation and transpiration, we have to just subtract from 1. What we did, we pooled data, means the data we extracted for all 19,000 plots. We pooled that treatment effect across all AWD intervention and followed outcomes through time. What we find that improvement in irrigation efficiency do not disappear immediately after implementation. Instead, positive impact remains visible across multiple growing seasons. What you see in the graph is basically, it is consistent, the finding is, our T by ET estimation is consistent with RCT evidence. And AWD effect concentrated in January to February and then declined March to April, which is again consistent with the field observation. The next slide, this one, this is also very encouraging for us. Across the different treatment arms, treated area generally exhibited higher T and ET ratio relative to control areas. In other words, a larger share of water is being used by crop rather than lost to evaporation. But effects fade over time and are about half as large as by 2023. So in the graph, what you see, that shows that once the intervention was applied, it continuously stayed for next 2-3 years, but then it started declining, and it declined a little bit by 2023. And now, for a few key observations. So what our finding through ET estimation is consistent with the ground observation RCT. And that is the main point here. We wanted to know if we can use Earth observation to track, monitor, and evaluate AWD in the AWD application in the ground. So this work is almost, obviously, more than 90% is complete, but there are a few things that still left to understand a little bit more in detail, and that is understand how all this is related to cultivation of the command areas, and what are the mechanisms that explain these outcomes, different outcome efforts. And this is, as I mentioned earlier in the presentation, that this is one of those use cases that literally require us to go out of our comfort area and find something that is truly can be applied and estimated and evaluated. So that also shows that how Earth observation can be used to do such kind of work in the field, and much more cost-effective And in fact, it can help us understand whether impact persists, scale, and vary across landscape. And with this, I will conclude that the broader lesson is that the Earth observation is not a replacement for impact evaluation. Rather, it is a powerful complement that helps us understand whether intervention persists, scale, and generate measurable environmental change. Thank you.
Thank you both very much. Next up, we have a session on scaling leaf color charts among cotton farmers in India, presented by Tomoko Harigaya and Yuntian B. So Yuntian B is a geospatial analyst in the Research and Evaluation Unit at AidData from the College of William and Mary. As part of the geospatial analysis team, she develops and implements geospatial workflows and programming to transform remotely sensed imagery and open source data into insights on social, ecological, and environmental issues. Her work focuses on geospatial impact evaluation, remote sensing, and applied spatial analysis in data-scarce environments, particularly evaluating agricultural land environmental interventions using satellite imagery and quasi-experimental methods. And Tomoko is the chief economist and director of research at Precision Development, a global nonprofit that scales innovations that millions of farmers can use to improve their livelihoods. So take it away, my friends.
Thanks, Matt. Okay. This podium is way too high for me, but so you can't see me, but hi, everyone. It's really great to be here and really appreciate the opportunity to share our work. So in the next 20 minutes, Yuntian and I will share our work in progress on the impact evaluation of leaf color charts, which is a simple tool that helps farmers optimize or improve the efficient use of nitrogen fertilizers. So this work is in collaboration with the AidData team and Jagori Chatterjee and Malek Jagnani. Is this a... So I'll cover the motivation of the study, the design of the two field experiments, and preliminary analysis using the primary data that we've collected on the ground. And then I'll hand over to Yuntian, who will talk about the application or the potential application of satellites to improve the relevant outcome measures here. And then I'll come back at the end to share how so far satellites have added to the evaluation. And so this is a very early stage work. The analysis that we'll present are preliminary and incomplete. So, we really look forward to any feedback and suggestions that you have. Okay, the motivation, I think it's now very well documented that returns to fertilizer vary a lot across plots, depending on things like soil properties, soil health and plot conditions. So it is difficult for farmers to figure out on their own how much fertilizers they should be applying in a given season. And it's not just underuse that's problematic, but overuse has huge environmental costs. And especially in places like India, where there are heavy subsidies for fertilizers, it just makes it easier for farmers to over-apply. And a leaf color chart is a simple tool that was developed by IRI maybe over 20 years ago now. As you can see in the photo, it's a panel with different gradients of green, and the farmers can just take it to the field and compare against the leaf colors. And each of these green panel has an associated urea recommendation that changes over the course of the season. So if the leaf color is already dark, then it advises farmers not to apply any more urea. It's relatively easy to use, more affordable than something like a soil test. And when we started piloting this a few years ago, we also looked into digital LCC. There's quite a lot of investment in there, but there are, at least at that point, technical issues of color calibration to get the colors right on different types of phones, different camera qualities and so forth, that seemed like quite difficult to overcome. So in this evaluation, we are focusing on the physical leaf color chart. And So LCC actually already has RCT evidence from Bangladesh with rice farmers maybe 10, 12 years ago. But the evaluation was fairly high touch, with working with a nonprofit on the ground, and then relied on self-reported data. When we piloted with cotton farmers in Gujarat, we got the same indication that a lot of farmers who were using LCC reported lower fertilizer use without compromising yields. So our starting point was figuring out whether there is a viable model for scaling. So our experiments focus on incentive structures to encourage adoption of LCC. And the broader ambition here is to assess whether LCC adoption could form a basis for payment for ecosystem services, or PES. And that's where satellites could potentially be helpful to have measurements at scale. So 2 experiments, we have selected settings where we expected overuse of urea. First, cotton farmers in Maharashtra during rainy season, and then second, rice farmers in Orissa in Rabi or dry season. So the structure of the first experiment, let me just first explain the design logic. The PES contracts often, or not often, but sometimes have this clause saying, we reserve the right to recover the payments if you don't comply. And we wanted to test whether that commitment framing could drive behavior change beyond payments. So we have the control group that got nothing. The first treatment arm was LCC plus light touch training and advice only. Second treatment added a conditional payment on compliance, which was verified by a leaf color check, spot check twice in the season. The third treatment arm was unconditional upfront payment, no strings attached. The last arm was the upfront payment with this return clause in the contract saying we reserve the right to ask you to return the money if the LCC spot check didn't show that you didn't use the tool. And let me just, so this is just a background on the soil nitrogen distribution at baseline for agronomist experts in the room. On average, the plot has a low nitrogen level and required 53 kg per acre of nitrogen over the course of the season. I'll jump right into the key result. So these 2 panels are looking at 2 outcomes: mean chlorophyll meter reading and number of optimal LCC readings out of 12 leaves per plot that we checked twice in the season. And so both of these are essentially measuring whether the crops were in the right nitrogen range, right? But through different tools. So one is the sensor instrument, chlorophyll meter reading, and then on the right is the LCC itself. And as you can see, many of the treatments didn't work, except the last one where we added this return clause saying, we reserve the right to ask you to pay us back if you didn't use the tool, and that increased compliance. So that's interesting. This commitment framing worked when farmers received something and they knew that they might be asked to pay back. It increases compliance. And from the scaling perspective, it's actually, it's encouraging, because if the behavior change is driven by the chance that you might have to return the money, then you might not need this full-blown verification process of individual farmers under the conditional payment scheme. Like you could do with maybe a lighter version where you say, we reserve the right to ask you to return the money, and there's some probability of being verified. And that reduces the cost of the program substantially. So that's the key result from the first experiment. And so we designed the second experiment around this result, just took the tool to a completely new setting with new value chain. And we removed the LCC-only arm, added the return clause to every financial treatment arms, but we varied 2 things. First, we varied whether we told the farmer that the results of the LCC spot checks would be visible to their neighbors, or they would be strictly confidential. And this is to test whether perceived social pressure or social image concerns added to compliance beyond financial incentives. And then second, we varied whether farmers received cash in hand or promissory note for the bank account to test whether having something tangible to lose would matter here. So that's kind of classic loss aversion. And then, so what we have is a very preliminary result. We've been just compiling the data that we've collected over the last couple of months. So here, just looking at the treatment effects on chlorophyll meter readings at 2 different points in time over the season. As you can see, like, there's nothing here. So we are not replicating the results from the first trial when you just look at the average effects. And when you introduce satellites, it turns out there's something more to that and more interesting, but I'll hold off and maybe hand over to Yuntian now to talk through the satellite application.
So here, I'm gonna briefly introduce how we apply Earth observations for both studies. For agriculture monitoring, there are several spectral bands that are sensitive to vegetation greenness and chlorophyll conditions. In general, chlorophyll absorbs red and blue light while reflecting the green light. Beyond the visible spectrum, red edge band and the near infrared, what we call NIR band, are both sensitive to vegetation conditions. Therefore, there are several satellite platforms that can potentially be used for agriculture monitoring, including the Sentinel-2, Landsat, and the Planetscope. Here, we initially started with the Sentinel-2 because it provides a good trade-off between the image availabilities and also the temporal and spatial resolutions. For both studies, we calculated several vegetation indices, including the NDVI using the green band and the red edge band, also several chlorophyll-related indices. For both studies, we calculated the mean and median VS for each field during the visit windows. So for study 1, we have the field boundaries for each farmer's plot. So the VIs were aggregated at the farmer's field level. But for study 2, we only have the point location within the field. Therefore, those VIs were extracted at the point location only. One of the most critical steps when we calculated the vegetation indices is that we have to remove the cloud pixels before the analysis. Because of this, the weather condition can strongly affect the, how many images we can get and also the image qualities. For study 1, the in-situ collections occurred during the monsoon seasons with heavy rainfalls and also the floodings. Lots of fields are fully covered by cloud as shown on the left. After removing the cloud pixels, more than 500 observations were missing. Compared to the study 2, which is on the right, the in-situ collection for the study 2 were collected during dry seasons. So the cloud contamination was very minimal and only 72 observations were missing. After identifying the cloud issue of study 1, we tried several approaches to handle these cloud issues. For example, we extended the satellite query windows, including 1 week, 2 weeks, and 3 weeks around the in-situ visit date. A longer query windows enable us to have more images, but also it's introduced more noises, especially during this rapid crop growing seasons, and the vegetation colors can change quickly over time. We also combined various images sources, for example, the Planetscope, which have a near daily revisit frequencies. Thus, we hope to get more available images. However, because of the severe flooding and the persistent cloud coverage during the study period, the improvement was very limited. We also consider other approaches. For example, there are gap-filling models using the nearby pixels or imagery from nearby dates. But because of the weathers, the missing areas was too large to produce a reliable interpolations. And also using the images from previous years does not align well with our event study design. There are also other possible solutions, for example, using the SAR imageries, which can penetrate the cloud. But the SAR imageries are very sensitive to the vegetation structures instead of the colors, which is not very suitable for comparison with the chlorophyll meter readings in these studies. The scatter plot is between the chlorophyll readings versus the NDVI using the red edge band, which provide us the highest R-square value in study 2. The R-square value is relatively modest, but the satellite images can still be very helpful and compensate with the survey data for agriculture monitoring. Tomoko?
So while we kind of continue to explore this correlation between VI and chlorophyll meter readings, I just wanted to share a couple other ways in which satellites have already been helpful for the evaluation. And I don't think these are any new points, but the first one is very simple, that it just gives us more better and richer baseline data. And this is just looking at the VI measures from the before intervention 2025 across experimental arms. As you can see, they are not identical, pretty noisy. By itself, it doesn't invalidate randomization, but it will still affect the treatment impact analysis. So, we are controlling for these values. I think, if we add probably more seasons, before the intervention, it might have marginal value add in improving the precision and so forth. And I'll maybe okay. I'll just skip to the last slide. Oh, okay. Okay. Here is earlier I showed from the second experiment that we did not see any average impact, But if you think about the theory of LCC, you would expect actually the under-users to be moving toward the optimal and overusers to also be moving down to the optimal. So you might see more movements at the two ends of the distribution. So that's what we are looking at here. These are quantile regression plots, so looking at the treatment effects at different points across the crop health distribution. So you can think of the effects at the 10th and the 20th percentiles as the treatment effects for worst performing or least fertilized fields, and then the effects for the 80th and 90th percentiles as the treatment effects for the best performing plots. And if you focus on just a central estimate, dark blue line, between the mean chlorophyll meter readings and NDVI values, you see that the kind of pattern of the trend is similar, that you see the largest effects at the bottom of the distribution, and then they kind of fade away as you move up. But if you look at the robustness of 95% confidence interval, which is the light shaded area, it's the NDVI estimates are precise enough that these positive effects at the bottom of the distribution become statistically significant. And if you don't, if we remove the baseline VI measures, you don't get that, precision there. So this is what we have so far. I think maybe we'll leave with one question that, that originally we were thinking about this as a tool that could reduce overuse. Right now, with either of the measurements, we're not seeing any movements at the top of the distribution overusers. And it may be that this is just reflecting the true absence of treatment impact among overusers, but I think the question is whether these are the appropriate measures to be using to pick up small movements in overuse. Would love to hear the feedback. I think we just jotted down some questions for open discussion, but we'll maybe come back to this at the end of the session. Okay.
Wonderful. Thank you both very much. All righty. Final presentation of this session is Mutual Crop Insurance in Nigeria by Peter Nijforti and Kendra Walker. So Professor Peter Nijforti is a professor of agricultural economics at Ahmadu Bello University, Zaria, Nigeria, with extensive experience in agricultural policy and development research. He served as principal investigator for the Feed the Future Advancing Local Leadership, Innovation and Networks, or All-In project at ABU Zaria, leading efforts to strengthen local leadership and foster innovation within Nigeria's agricultural sector. And we also have Kendra Walker. She's a remote sensing scientist who holds a PhD in resource policy and management from the University of Michigan. For the past 5 years, Kendra worked with the Environmental Markets Lab at the University of California, Santa Barbara. She's currently a consultant on various international projects where she builds remote sensing pipelines to evaluate policy uptake and effectiveness. Kendra's current cloud-based work is grounded in extensive on-the-ground field experience in Panama and Gabon. So thank you both, and let's see what you got.
Yeah. Good afternoon to everyone. My name is Peter Nijforti. I'm presenting on this topic, adapting to climate risks with mutual weather index crop insurance in Nigeria, a frame field experiment. And my co-presenter is Kendra Walker. This is the work we have done from 2022 to 2024. Using the traditional method of survey to actually collect information as we use the enumerator. And Kendra is actually working hard to validate what we have done using AidData or GIS device to actually do the analysis to validate what we have done. And so that is what we'll be doing. So here I will start what I'll be doing. I will just present this an abridged version of event. So I'll be giving a brief background information and then the study designs and then some of the key findings and the lesson we have learned and then some of the recommendations we've made. Then before she comes in with the GIS aspect. Now, going to the background, the climate risks is actually a very big problem in the northern part of Nigeria, more especially in the belt called the Sudano-Sahel region. And it is manifest in the form of high variable rainfall, where rainfall is just between 300 to 600 millimeters per year. And there's frequent droughts. And even during the cropping season, you have dry spells that may make farmers to lose their crops. And there's rising temperature. So, and majority of the people in the axis are small-scale crop farmers and livestock farmers. So anything that affect the weather condition of the climate indirectly affect their livelihood. Now, this challenge has been underscored by some of the major media houses, international media houses like BBC, Al Jazeera, Prime Time, by interrogating some of the farmers, like the first farmer that BBC interviewed said he has lost all his crop due to drought and due to flood. And it is similar pattern for almost everybody that is being interviewed in that axis. And so, again, another issue in that area is that the population are predominantly Muslims who practice Islam and the Sharia law. And the religion seriously influenced their belief system, such that in the coping strategy against climate change, they put prayers as one of their coping strategies. Outside crop diversifications, informal mutual aids, asset accumulations, and others. The other thing they do is when there's prolonged or when the rain probably doesn't come on time, they go into praying for the rain to come. And most often when they pray, it rains, and it tends to reinforce the belief system. Probably the prayer was at the time the rain was about to fall. And so the coping strategy adopted by these people in this axis hardly address the covariate shocks introduced by climate change. And more to that, there is actually complete absence of conventional insurance in the area, simply because the conventional insurance is not in compliance with Islamic finance, which seriously deters excessive risks or excessive speculations and interests. And so the people in the axis do not actually accept conventional insurance. And that is the reason why the team from Ahmadu Bello University experimented using the mutual weather index crop insurance to see whether it can address the climate change challenge faced by crop farmers in this area, more specifically sorghum and millet farmers. Now, mutual weather index insurance is a Sharia compliance insurance, which is based on mutual cooperation and shared responsibility, where participants contribute to a pool of funds for the compensation of losses. And so this insurance is actually very promising in addressing the climate change problem that farmers in this axis are facing, because it is actually based, or it takes into consideration Islamic finance by actually avoiding issue of interest and excessive risks. And then it actually measures the risks based on index of weather instead of individual crop losses. So the transaction cost of evaluating crop losses is very low. And so based on that, I strongly believe that this insurance policy is obviously going to address the risks that farmers in these areas are actually experiencing. Now, the study design, this study actually was conducted in 7 states, 70 communities, 955 farmers who were assigned into 3 experimental groups. That's, you have 2 experimental groups and 1 control group. Now, looking at the roadmap of the project, in May to June 2022, baseline survey of 15 farmers and villages were conducted. And then in April 2023, risk management training and enrollment was conducted. Then again in 2023, picture protocol plus weather monitoring was equally conducted. And in 2024, we had the end-line survey and impact analysis. Now, again, I said the study area, there are 7 states across Nigeria. There are 7 states across the northeast state are Kebbi, Sokoto, Zamfara, Katsina, Kano, Jigawa, and Yobe. Now, village selection criteria, villages were selected within 50 kilometers from a functional weather stations, and this actually was to ensure that data on the weather, either rainfall or temperature, can be collected. And then the population of the community where these villagers were selected should not be less than 500 residents, so as to have enough in the sample group. And then the crop considered were millet and sorghum, because they are the dominant crops planted in the study area, because it has very short rainfall, so these crops, they have short gestation period. And then the villages should have route access all year round, because there are some of the communities there that so we selected villages that we could have access to them any time of the season. Now, as I said, these members that were selected were assigned into 3 groups. The first is the control group. The control group was neither enrolled in the conventional insurance nor in the mutual weather index insurance. And then the second is the first treatment group, which is the mutual weather, or which is the weather index group. These were farmers that were enrolled into the conventional insurance, that is Nigerian Agricultural Insurance Corporation. And then the third arm are those that were enrolled into the mutual weather index insurance, and they were provided with some financial literacy and some additional information. Now, the key findings we had was that mutual weather index insurance lift future TACAFO participation. For example, we found that the mutual weather insurance has 7.7 percentage point increase in the number of participants in the mutual weather insurance group that are willing to take part in future mutual weather index insurance. But we had some heterogeneous disparity across the state. For example, in Jigawa State, the number of people that actually indicated willingness to participate in future mutual weather index insurance was about 9.5 percentage points, followed by Sokoto, Kanu, and Yola. Now, the treatment effects of the insurance outcome, this was investigated between the two treatment groups, that is the mutual weather index group and the conventional insurance group. And the result on this table, as you are seeing, though generally mostly counterintuitive, but one thing stands clear. For the future TACAFO participation in the mutual weather index insurance, it shows a strong positive effect on future participation by participants into this particular insurance. Now, what lesson did we learn? Now, what drives and limits mutual weather index insurance adoptions in the Muslim farming communities? One is religious compliance matters, meaning that any insurance product that you are to introduce to these people must actually meet up with Islamic finance. It should not incorporate issue of interest and excessive risks. Secondly, the other lesson we learned is that geography shapes uptake. We have realized that even though generally there are more participants willing to uptake the future TACAFO insurance in the mutual weather index group, but we find some geographical heterogeneity or disparity, whereby we saw that in Jigawa State, most people indicated, or most of the participants indicated that they are likely to take participate in future mutual weather index insurance. Then again, education moderate response. We realized that people with strong education background actually indicated strong willingness to participate in future mutual weather index insurance. And implementation quality is equally decisive. How we implemented this project equally matters. Now, what conclusion and policy recommendation did we draw? We concluded that the mutual weather index insurance is a viable plan for climate resilience in northern Nigeria. Now, but the key recommendation we made was that priorities should be given to the TACAFO compliance mutual weather index product with Sharia compliance, because it's compliant with the Sharia law. And then target those key states that show strong willingness by the participant to participate in the mutual weather index insurance. And then invest in comprehensive farmer educations and local language training, because we realized that those with strong educational background actually indicated high willingness to participate in future mutual weather index insurance. And then recruit experienced farmers as ambassadors, use peer-to-peer learning. So those farmers that shows leadership could be recruited to actually take the lead in spreading the good message of the mutual weather index insurance prospect for addressing the climate change crisis in the zone. And then build enabling policy, TACAFO regulations, subsidies, and weather data infrastructure. So generally, mutual weather index insurance can be the cornerstone of climate resilience agriculture in the Sudani area. So, Kendra.
All right, thank you, Peter, for laying out the framework of the RCT and the lessons learned from the RCT. So I joined this project to look at the potential for satellite-derived condition estimates to inform crop insurance initiatives, such as this one. Satellite imagery can support crop insurance initiatives in many ways, primarily by informing the index-based payments. As others have talked about, satellite imagery can be much less expensive than field visits, especially in northern Nigeria, which is very prone to violence. Also, using satellite imagery could lower the demands on farmers compared to like the picture-taking protocols that are currently used. Also, satellite imagery can provide context regarding baseline conditions and farming effort, so not every plot is expected to produce the same yield. So we can gather those insights from remote sensing, and we can also reduce moral hazards that might be part of, the insurance framework. If you're expecting to get a payout, you might work a little less. And so we can kind of monitor the field across time to control for those things. And finally, remote sensing data can provide critical information to farmers, so they themselves can decide whether or not they want to participate based on more information, or they can reduce their damages regardless. So for satellite imagery to be useful, we need to have an index that is sensitive enough to changes in damage, and that needs to use publicly available satellite imagery, so generally Landsat or Sentinel. We also need georeferenced field data for the farmers, preferably in the form of field perimeters. That could be flexible. And we need linkage data to reliably connect the farmers to their fields. That turns out to be a problem in a lot of projects. And then finally, we need training and validation data to be able to test indices and see their reliability before we try to implement them in the real world. So this project has provided these components that makes for a great preliminary analysis. So they have 813 final participant surveys, which provides data from, these are self-reported farmer reports about the damages on their fields and the types of damage and the levels of damage. There are also 544 georeferenced fields. And so far, we've been able to link 300 of those fields to the participants. We're still working on sorting that out, but that gives us a good amount to do a preliminary analysis with. So the questions of the preliminary analysis are whether individual plot performance can be gauged with a simple index, and whether the levels of damage reported by the farmers are detected in the satellite data. And then also a basic RCT validation of whether there's a difference in the arms. So regarding the first point, we see that there is great potential to gauge the performance of a field with publicly available data. I'm not really going to go into the processing pipeline, but it's pretty simple, just using all the Landsat and Sentinel data available. This is Sentinel-2, we could add in Sentinel-1 SAR imagery, but we found that there's pretty good performance with just optical. And then normalizing that, harmonizing it, and basically turning it into smooth time series signatures. So these are 4 different indices. They all show similar information with different levels of detail. But you can see here, so this is a single plot, but this plot was certainly less productive in 2023, which was the year of the RCT, compared to other years. So those differences do come out in the data. This is just looking at different farmers' plots, similar results. This is a quick aside, but in the RCT validation, these are the three arms of the RCT, and we don't see any significant difference between them, but that's actually a good thing in this case. So usually we're looking to see differences, a treatment effect. But in this case, the treatment effect is affecting the uptake of insurance, not the exposure to damages. So this is showing actually that there's no bias in the exposure to damages, which is a good thing for this project. So back to looking at whether we can detect the damages. So this is showing that there is a difference between, for example, the no damage, which is the black line, compared to the total damage plots, which are the yellow line. There's a significant difference there. But one thing I want to point out with this is there's also a significant difference from the beginning prior to planting and also post-harvest. So these less damaged fields tend to be in more fertile areas. This is just adding the confidence interval so we can confirm that, yes, the difference is significant. The difference is significant also in the amount, in the peak production, although there's something very interesting going on with the total damage, which is that it actually rises later in the season. And this is because a lot of the farmers are actually able to plant after the damages and to harvest later in the season. So that's something that needs to be kind of pulled out. Obviously, on an individual basis, that would look different if we're plotting each farmer's plot. But another thing about this, this type of analysis is, this is just, the x-axis is just the day of the year. So we're putting all the plots together, regardless of when they were planted. I mean, they're all the same crops being planted in the same season, but still there are some differences in when the farmers plant. So when we normalize this to days from planting, which we have that data thanks to the farmer interviews, then we can see even more nuanced differences going on here. We're going to ignore the yellow line because we don't have time, there's a lot going on there, but looking at just in general, we see that there's definitely a difference between the healthy crops that experience no damage and the plots that experience damage, but the main difference is really in the timing of the peak rather than the height of the peak. So that brings out many other questions of what's going on here. One quick insight from this is that there's no difference in the actual rainfall for the different groups experienced damaging. So this is using CHIRP's rainfall data on the left, and there's no significant difference between those groups. However, the significant difference is in the timing of the planting. So the people who planted later were significantly less likely to experience damages. And also the kind of lighter yellow color, the big peak there, are farmers who experience both low rainfall and flooding. So if you plant in the wrong time, you get all the bad weather. So the main conclusions from this preliminary analysis is that variation in land quality and farmer behavior are leading causes of yield damage. So the healthier crops are on land with higher vegetation indices even prior to planting, and the timing of planting heavily influences the crop's vulnerability to damages. So we could see how satellite imagery could be used to further potentially help out farmers to figure out the optimal period to plant in. There's definitely potential to track field production and damages using satellite imagery, but we still need to kind of sort out a lot of things using ground data, primarily whether those peaks that we're seeing at the end after damages are crops that could be harvested, or is that some kind of weedy growth that is not actually useful to the farmer, which is very important to know when assessing the farmer's loss. And a key takeaway from this project is that we need to prioritize coordinate and linkage protocols to help make the best use of this really high quality ground data that is being collected so that we can link it to the remote sensing data in the future. And, oops. Oh well, that's what we had. Lost my slide, but.
All right. And how about a quick round of applause for all the presenters? Great job. So, thank you. And so we have a few minutes to allow for some questions. So we'll do it the same way that we did before. If you just want to raise your hand quickly, if you already have a question, so we can get a sense of how many. All right, cool. All right, we'll start with you. Anthony, you know the deal? There you go.
Great. Anthony D'Agostino from Mathematica. I have a question for Tomoko. What are your sort of working hypotheses for why we don't see reductions in fertilizer use at the top end of the distribution? Is it concerns about fertilizer runoff with like rainfall events? What are some ideas that you guys are considering?
Yeah, I think it's possible that there's the quantity of total fertilizer have changed, but they are ending up with the same results, right? So, but we haven't analyzed. We just wrapped up the data collection on fertilizer use, which has information about the timing of fertilizer application, quantity for each application. So that might give us some insights on whether even if the crop outcomes are not different, if there's a change in the quantity of fertilizers that farmers used. I think that's probably the primary hypothesis that I have in my mind. But if you have other kind of thoughts, please do share.
Great, thank you. And Matthew, if you want to go ahead.
Sure, it's for Kunwar. I was just curious if you had enough data to use the electricity bills as your dependent variable and relate that to hydroperiodicity of the rice. So go straight to the variable of interest, money.
Thanks, Matt, for the question. Yes, I think there's enough data, but data is a little uncertain in quality, so that has led us not to go in that route yet. When they were recording the data, there were a lot of missing details, and they were not sure if they are correct. That's right, and that's also total electricity bill at the end of season. That's another reason we are unable to use these as a dependent variable. But I think the approach we have taken, this could be a very good, in some new places where they implement from the scratch, could be done from very beginning, yes.
Cool, thank you for the question. Any additional questions? If not, I do have one myself. Seems like we need a little bit more coffee or espresso here, folks. We got one right here. Please, go for it.
Okay, thank you for the great presentations. So I have a question to Tomoko. The organic fertilizers are they also considered in the treatment and control group selection? And also, I just wanted to understand which type of crops the farmers do focus on a specific crops they grow, or all types of crops?
Sorry, the first question was about organic fertilizers?
Yeah.
So, okay. So in this particular setting, not many farmers are using organic fertilizers. So at baseline, we collected detailed information about all the fertilizers that farmers were using. I don't recall. So there's a small proportion, say less than 5%, using manure, right, homemade organic fertilizers, but nobody is purchasing organic fertilizers in this setting. And then so the crops we experimented with are cotton farmers in the first experiment, and then rice farmers in the second experiment.
All right, any hands? Yes, sir.
Thank you. Maybe one more question for Professor Walker for the last presentation. We really understand the issue of finding reliable data on field boundaries and the linkages between boundaries and beneficiaries or households in general. But more and more we see the increase of the availability of alternative data sources on boundaries of fields generated through machine learning at scale. We have seen several data sets being released at global scale quite recently. I would like to know if you had the opportunity to explore those data sets. Any of them, there are already a couple of them that are available since quite a few months already. And if you have any experience with that, if that could be like possible alternatives. Thank you.
Sure, thank you for that. Yeah, I'm in various work. I've worked on a lot of field segregation, different methodologies, and I think the main issue with that is, I mean, it's regionally specific. It depends on what you're looking at. So crops in the Sahel are very hard to actually identify the perimeter to, even looking at oneself on high-resolution imagery. So it's very difficult to determine where one's farm would end. That aside, the primary issue beyond that is just actually linking a given plot to a farmer that we have information for. So when that data gets lost or somehow isn't, we're not linking the two up. I mean, from machine learning, we wouldn't be able to link the plots up to the farmers. We need somebody to actually be visiting on the ground to identify whose plot is who. So that's really the primary issue we're having, and then finding the actual boundary is kind of a secondary issue.
Yeah, it was a great question. I was thinking as well about like the Taylor Geospatial Institute's recent release of the field boundary data, but that makes total sense, Kendra. I actually had a really quick question for you and Peter as well. And so I was wondering, like, I could see potential hesitation on the farmer side of going with this remote sensing based sort of indicator of stress, right, that would result in the insurance payout, and them viewing it as this kind of black box, right? Like I see people in the US with hurricane insurance, and they're just getting these like, AI outputs that the insurance company says, yes or no, we validated it. Have you seen any sort of like, or do you see hesitation in the communities where they say, whoa, like we know when it's damaged, why are we letting a satellite tell us when it is or is not?
Okay, I don't know these communities. I
can
respond in general, but I think that's a very valid concern. I think that would be the next step probably is, once we had a product that we feel pretty confident in, so far I don't think it's fair to just say, oh, the peak value means that, your crop was good. Yeah. Because it could just be weedy growth or something else. So we need more data behind that. But once we had a product we're confident in, the next step would be for the team to take it out to the community and see how it's received.
Got it. Thank you very much. All right, y'all, keeping on time here pretty well. So thus ends our third session. We have 30 minutes for coffee, tea, networking, etc. We'll see you all back here at 4 p.m. Thank you.
With session 4. If everyone can make their way back into the room, that would be wonderful.
Yeah, Matt, grab people. Matt's it.